As we continue our study of geometry, we've looked at formulas for area and perimeter of different shapes, and we've put several together for surface area. Now we need to fill our containers. That's volume. So here we have our cube, which is our square, repeated. When we did surface area, we unwrapped it and found that we had 6 of these faces of a cube to find the surface area. Now we're going to fill this container. So the amount of, let's say, sand we could put at the bottom of this container would be the same amount as in the center and on to the top. There is no wasted space in this particular shape. So our volume is side cubed. Basically, you're saying length times width times height in this, but it's all the same number because we're working with squares. But you could use the same formula we have for a rectangular prism, this box, perhaps it looks like a tissue box, with length, width, and height, and still get the right answer. But that's more sophisticated formula for volume of a cube. The rectangular prism can be shown like this, or it can be shown like this. Volume is equal to a capital B with an H. Now the capital B is really going back to the area calculation. So when we were doing area of a prism, we did basically this length times width. So that would translate to this B, this capital B. Length times width, and then we put the height onto it. Do you see in each of our formulas, when we have gone to the volume, we've added the height, 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 and all of these are heights. That is the next dimension that gives you a container. The cylinder. Okay, that's this cylinder. As you can see that if I filled this cylinder, let's say we put some marbles in here, we would have the same amount of marbles in this layer of the can as we would in the middle, as we would at the top. There is no wasted space in that. You can tell because the lid and the bottom are the same size. So in our cylinder, we have no fraction. We're going to fill up this can. That would be volume is equal to pi r squared. That's because we're working with circles for the top. The top of our can and the bottom are circles. So we're going to use the area formula, pi r squared, and then multiply it times the height. Because once we know what the circle measures, then we have to know how much we can fill in this, the height of it. So no wasted space in the cube, no wasted space in the rectangular prism, no wasted space in the cylinder. There's no fraction in any of those formulas. The base, the big capital B on this one, stands for this much of our formula. A pyramid now has a square base, but it narrows up to a peak at the top. That means we would get, if we filled this container, we'd have more sand or marbles on this bottom part than we could fill into the peak of it. There's less space up here. So we have a fraction in this formula. It's a three-dimensional figure, so our fraction has a 3 in it. That's how I remember it. Volume equals 1/3 length times width times height. And the capital B in this one stands for this much of it. A cone also has more space at the base than it does as we travel up to the peak of the cone. So again, that one has a fraction in it, 1/3, because this is a three-dimensional figure. We have the pi r squared in here because the cone has a circular base. And of course, we need the height from the middle of the base up to the peak. In this figure, the capital B stands for this much of the other formula. Now, when we get to the sphere, that's like a basketball or a soccer ball, beach ball. Now we're talking about volume is 4/3 pi r cubed. So this one is a little bit different than what we've seen before, but that's because we're working with circles. These are the volume calculations that you're going to see most often.